Here, after talking about k-nearest neighbors in great detail, let us finally get to the fun part of this lecture, k-nearest neighbors in Python. So what I'm going to show you is a code example I made implementing k-nearest neighbors using the scikit-learn library. Not all of it may make sense at this point. The next lecture we will talk more about Python and NumPy, also about scikit-learn. So right now this is maybe more like a teaser. I will go through some of the concepts already, but if you feel that's a little bit too complicated at this point, you can also watch the video later after we discussed NumPy and some of the scikit-learn basics. But I thought maybe it's a good opportunity here to give you a top-down view of how these tools work. So I will go to this website here and download also the code examples from here. So yeah, that's the website. So we have right now in kind of more interactive session instead of doing the slides. So I set up a GitHub repository for this class, and the reason why I like uploading things to GitHub is because it's also like a real world tool. So I just see I should fix this line issue. There's everything on one line. Okay, doesn't matter now. I don't want to get distracted now. But yeah, GitHub is a tool that most machine learning researchers use in practice. So it's kind of good to become familiar with it because many people upload their code there if they write papers and things like that. And I also heard that a lot of companies nowadays, they ask for your GitHub profile when you send in your CV or resume. So yeah, it doesn't hurt to build a portfolio on GitHub at some point, maybe even uploading your class projects this semester if you have some cool projects that you want to share. So that's always a good idea to share it because yeah, recruiters may want to take a look at this at some point. Yeah, if you want to download things from GitHub, if you go to a repository like this repository here, you can click on this green button here and there should be a download zip link and it will download the whole repository as a zip file. Now, like I said before, I will be updating this repository, and if you don't want to re-download the whole repository every time, you can also clone it. So what that means is we make a copy of the GitHub repository on our hard drive or on our computer, and then we can update it later on in this course. So I will also show you how that works. So instead of downloading the zip file, I will copy this link here, and then I will go to my terminal. So on Windows that may be a little bit different. I honestly don't know exactly how to do that on Windows. So I'm on a Mac here, but also the same concepts would apply on Linux. I think there may be good tutorials for Windows, and the TA can also help you with that because the TA is also one of my research students and he's also using Windows. So I will first go to my desktop because it's just a temporary setup here. And then I type git clone and paste this link. That's downloading the content. May take a while. So after it downloaded, we have this folder here now on the desktop. And if I open it, it's basically a copy of the GitHub repository. And there are some additional files or an additional folder. That's the .git folder. It just contains the basic Git history, Git log files, and so forth. So this is this Git folder is basically what makes it a Git repository. And then once I've done that and I navigate into this folder, I can in future update it by doing git pull, for example. Right now it's up to date because I just downloaded it, but let's say next week you want to get the latest update, you can just type git pull and it will only download the changes. It won't re-download the whole folder. Now to show you the code examples, I will make a copy of that because I don't want to modify it, because if I would modify it here and then I would type git pull, what will happen next time is that it will get maybe some conflicts because we changed something and it doesn't match the version that it's pulling anymore and so forth. So I'm making a separate copy on my desktop here. And then I'm navigating into this folder. And we will be using, oh, sorry, that was the wrong one. I have a code folder also somewhere else on my computer. So I'm now on this folder, and there are two files, IPYNB file, which is an IPython notebook file. It's called Jupyter Notebook nowadays. Back in the day, it was called IPython Notebook. And there's a text file, a CSV file to be precise, and this contains the Iris dataset. I know not everyone is excited about the Iris dataset, but I think for the first example, code example, I wanted to pick a very, very easy dataset, because then we can focus more on the tools rather than understanding the data. And the Iris dataset is something I introduced in lecture 1. So in that way, we don't have to spend too much time on exploring a new dataset, because that's just like a dataset we covered before. And here we can then now focus more on the tools, the machine learning tools and the code. So I will start Jupyter Notebook. I use actually Jupyter Lab, which is a flavor of Jupyter Notebook. It's like a newer tool that is a little bit more fancy than the regular Jupyter Notebook. Yeah, so let me start it here. It will open up in my browser by default. And then I can open it here. Now let me clear these outputs here. So that I can execute them step by step and go through them step by step, so it's not overwhelming. So you will see the results while I execute them. And again, in the next lecture, I will talk more about Jupyter Notebook or Jupyter Lab, and will show you how you can set it up. Or actually, I will maybe also share some documentation on the GitHub repository, because sometimes it's just easier to have it in text, because then you can follow it step by step and copy and paste the commands and click the links and so forth. So usually what I like to use in my Jupyter Notebooks is an extension called Watermark, and that's an extension I made a long time ago, and it's just listing versions of certain software packages. The reason why I'm doing that is it shows me what versions of the certain packages I used the next time I execute that notebook. So if I get some different results, I can maybe see, oh, my version is now different than before, for example, and that may explain why the results are different. Or if someone has a bug or something, or if you have your homework and there's something not right, maybe it helps seeing what packages you used, and then it's probably basically based on the package version you used that there's a bug, and then we can make recommendations what to update and so forth. So let me execute this cell. It will show you your Python version. I'm currently still on Python 3.7. I recommend Python 3.7, 3.8 for this class. I think Python 3.9 will be released soon. It doesn't really matter whether it's 3.7 or 3.8. Either way, it should be fine. NumPy, SciPy, Matplotlib, and scikit-learn. Again, we will talk more about installing these in the next lecture. So if you want to install any package just from here, from the Jupyter Notebook, you can copy this command to install Watermark. So if you execute that, it will install Watermark using pip. That's the Python package installer. And there's another way to do that. It's Conda. I personally use Conda. That's like another Python distribution that has also it's better at managing a Python environment for usually data science. Nowadays, it's less important than it once was. Nowadays, using pip is also pretty good, but back in the day, it was trickier for certain packages. So Conda makes certain things more easy, and it also checks compatibility between certain packages. So some packages require some other packages, and then there can be conflicts that this version number is required for one package and another package likes another version of the software. And Conda usually finds the common denominator and makes it work pretty nicely. So you can also install it like that if you would hit enter. One thing I want to mention here is the Y. It just means yes. So, and the channel, what that means is there's a certain base channel where Conda packages are located. However, Watermark is more like a project I developed, and that is not important enough to include it, of course, in the basic Conda installation or Conda package repository. So there's a community maintained repository of Conda packages. It's called Conda Forge, and usually I would even say they are tested even better than the regular Conda packages, because the Conda Forge community has a lot of tools for checking that these libraries work on different computers and so forth. So it's just saying install watermark from this channel, from the Conda Forge channel. Anyways, let's not get distracted by installations here. So after we just check that everything looks okay, that we have kind of up-to-date software here, I'm importing now some packages that I will be using in this notebook. So these are my basic packages. We almost always need these packages like pandas, numpy, and matplotlib. Pandas is for data frames, numpy is for linear algebra and arrays, and matplotlib is for visualizing data, like plotting data. So I'm doing that. Oops. Next, we will be loading the iris dataset from the CSV file. So first I'm using this head command to just take a look at the CSV file. It usually looks like that. So the head command here is a Linux or Unix command or program that will show us the first lines of a data file. So in this case, it will show us the first 10 lines. It gives us an idea of how the CSV file looks like. So you can see there is a header line. It contains the column headers, the column names. There's an ID, sepal length, sepal width column, and so forth. And the last column is the class label, the species. And then we have the values here. Each training example is one row. So these 4 values here, separated by a comma, are the features, and the last column is the class label. So if I would do tail, there's also a tail. It shows me the bottom of this data set. So here we have Virginica, and in general we have 50 Setosa flowers, 50 versicolor flowers, and after that 50 Virginica flowers. Now we are going to load the dataset into pandas, into a pandas data frame. There's a read CSV function. It has a lot of options, but for this file we don't need to use any of these options. So this is how the file looks like or the data frame looks like after I loaded the text file, the CSV file. It's a comma separated file. CSV stands for comma separated values, but essentially it's a text file where each column is separated by a comma. So that's how it looks like. The tail command is similar to when I type tail up here. It's showing the last few lines. Here in pandas, the tail command shows the last 5 lines, but I can also show, let's say, the last 10 lines if I wanted to. All right. Yeah, that is just usually a good way to just double check that everything looks okay. So in machine learning, we usually use NumPy arrays instead of data frames. However, recently scikit-learn also started to support data frames, so we could technically use data frames too, but I personally, it's just maybe because I'm traditional, I like to use still my NumPy arrays, which is maybe more the classic approach. And if you use this, so let me go one step back. If I use this command here, I will extract certain columns from the dataset. So here I will only extract the petal length column and the petal width column, which are this column and this column. And I'm just doing that first to just demonstrate how you can extract columns, and second to make the dataset a little bit easier for our first machine learning example here. So if I do that, I will only get these 2 columns here. Yeah, and the values will give me the data frame version of that. Sorry, the array version. It will be now a NumPy array. So this is now a NumPy array. Looks a bit more bare bones now. So you can think of it also as a matrix, n by m matrix, where n is the number of training examples and m is the number of features. In this case, it would be 150 training examples and 2 features. So the shape command will confirm, or basically what I just said, the shape command is showing me the number of dimensions and the number of entries in each dimension. I should execute this first. So it shows me, well, it's actually the same it shows me that this data frame, this array consists of two axes or two dimensions. The first dimension is the one on the left here, and this is the second dimension. So the first dimension has 150 entries, and the second dimension has 2 entries. So that is in the matrix, the n by m. It's a 150 times 2 matrix in this case. So you can, if you wanted to, you can also just get the number of dimensions like this. Ndim, I think. So it is the number of dimensions, but usually I never do that because I can usually count 1, 2 here. So it's kind of overkill to execute the ndim command to get an idea of the data set. So here this also gives me an idea of how many values are, or how many entries are in each dimension. And in NumPy we call these dimensions axes, like axes. So yeah, with NumPy we can also do indexing like with Python. However, we can have an index for every dimension. So next lecture I will talk more about how that works in detail in NumPy. But just briefly here, this gives me the first 5 rows. It's basically the same as writing this row 0 to 5. Note that in contrast to R, you probably have worked with R a lot in statistics. In contrast to R, Python starts at 0 with the index. So this will give me the first 5 rows. And if I have this colon here without any values, it means all of them. So that will give me all columns, in this case 2 columns. So yeah, I'm essentially printing out the first 5 rows of my array. It's just to visualize it or just to double check that it looks okay basically. Yeah, another traditional aspect of machine learning in Python is to have class labels as integers instead of strings. Nowadays, I think also scikit-learn largely supports strings as class labels, but again, because I'm traditional, I'm also doing it the old way, converting the strings into integers for the class labels. And that has the advantage if you are using tools that are somewhat compatible with scikit-learn. So a lot of people develop algorithms that work with scikit-learn. Not all of them are so strict and allow you to use basically strings. So they don't really ensure that everything is totally compatible. It's always, I think, a good idea to use integers because that should always work. So what I'm doing here now is I'm using the pandas data frame with the map function to convert all the string class labels into integers. So I will be using a 0 instead of iris setosa, and I will use the 1 instead of iris versicolor, and I will use a 2 instead of iris virginica. Yeah, so this whole thing is a Python dictionary, and there's a map function. The map function is like a programming concept. It exists in different languages. You may also know that from R or different languages. I'm just mapping one thing to another thing. So, and this is essentially my mapping dictionary. So what I'm going to do now is I'm applying something to the species column. The species column is my class label column, just to show you how it looks like again. It's just my class labels here. So iris setosa until iris virginica. And I'm going to replace them. And the map function will take, so if it sees basically iris setosa, it will take this string and convert it to a 0. And if it sees iris versicolor, it will convert it to 1 and so forth. This is what we want basically. So after I executed this command, what we can see here is that we have a new column. It's called class label. So I was assigning a new column to this data frame. I call it class label. And this is basically the converted version of the species column. So let's just see what happens if I just execute it like this. So you can see now, let me use the values. Because if I don't use the values, it will be a pandas series, and that has this index here on the left, which is maybe a little bit misleading here. So this is my array, and you can see basically that is consisting now of the converted values. So if I don't do that, I will have my strings here in my array. So what I was doing basically, I was assigning this array to a new column just for reference. So the column is shown here on the very right now. And yeah, for scikit-learn, we also have a convention that we usually use the letter X to refer to the data set or the features, and the letter Y to refer to the class labels. So when I'm executing that, or this command, it will assign these values to a variable Y. Here, this is just the 10 first values, but we can take a look at all of them because they're small. So you can see these are my 150 training examples. You can just maybe make sure that it's indeed making sense. We should have 50 training examples for each class. So yeah, 50 for 0, 50 for 1, and 50 for 2. So in machine learning, we usually have a training set and a test set. Sometimes we also have additional data set splits like a validation set, but we will talk more about this in the model evaluation lecture. So here at this point, we are just dividing the data set into a training set for fitting the model, and then a test set for evaluating its performance. So first now in this step 4 here, I'm going to show you how we can do that manually, and then I will later on show you how we can do that in scikit-learn. So maybe let me hide this lower part because otherwise it's a bit distracting. Okay, so what we are going to do now is we are shuffling the data set first, and then we are dividing it. Why do we shuffle it? I mean, I showed you above that the class labels are sorted. So when we look at Y again, we see that the first half of the data set would be approximately here. We can actually show it like this. It should be 75, right? So these would be my first half, and this would be my second half. So if I would divide, if I would say the first 75 data points are my training set, or let's say the first 100 training examples are my training set, and the last 50 examples are my test set, what will happen is that the model during training only sees the two classes 0 and 1, and then during testing it sees an entirely new class, class 2. And that will of course not work because we usually assume that the training set has the same distribution as the test set. So what we will do is we will shuffle the data set first. So how do you shuffle something? I mean, there are many different ways. I personally like doing it this way. I realize there are different ways, but if I would do it manually, I would first create an index array that has the same length as Y. So I will just show you how that looks like. So it's just an array from 0 to 149. Okay, that's right here. And then I will shuffle it. So I'm using from NumPy this random state object. There's also a different way you can do that. It's NumPy random seed, I think, that can also set a random seed. And a random seed guarantees that you get the same results every time you set the random seed and execute an operation. And I think it's not really necessary always, but most of the time I prefer that because it gives me like consistent results. If I want to double check my results, I make I tweak something in my pipeline. I want to make sure that I don't have any kind of randomness that changes when I execute my code again. So in that way I can make it reproducible. Or if I give you my code, you will get the exact same results I get, which is I think nice. So let me execute this. It will first of all initialize this random R&D object. It's a random state object. And then I will call the permutation function, which will just shuffle around these indices. So you can see they are shuffled now. Now when I execute this again, it will always create this same shuffling. If I wouldn't use a random state or random seed, you can see it changes every time. And now if then, for example, I get a certain result, I will give the notebook to you and say, yeah, here you can play around with that. You will get probably totally different results than I did. But if you use a random seed, the same random seed that I used, you will always get the same results. We don't have to use 1, 2, 3. It's just arbitrary. We can use also our favorite number, 42. If you know Hitchhiker's Guide Through the Galaxy, that's like a common programming joke. Anyways, so yeah, I just used 1, 2, 3 here for arbitrary reasons. It has you can also actually use a random seed manually like this. But sometimes when we make more complicated pipelines, especially when I work on my deep learning stuff, I have a separate random state for different parts of my code, and I like to keep them separate. And if you set the random seed like this, it's affecting all the code globally, which I sometimes don't want. But you can also use NumPy random seed instead of this one here. And I think I don't right now recall what the command is. Maybe random permutation, so something like that. Nope. Sorry, NumPy. Yeah, you could technically also use this approach. No. So this should give you the same as using this random state. I like doing it with a separate random state. Anyways, I'm getting distracted here again. Sorry. All right, so why did we shuffle the indices, and why didn't we just shuffle the label array directly? That is because we want to shuffle, of course, the feature array accordingly, right? So because each label corresponds to a row in our matrix X, so we have to reuse the shuffled indices. So what I'm doing now is, if I do that, it will shuffle around the different values in this array. So for example, before that, the index 0 was in the front. Is before we had like 0, 1, 2, 3, 4, 5. Now 0 is at a total different position and so forth. So it's just shuffling around all the labels here. So we can see it's now shuffled. And the same is true then accordingly for my X array. So it will also shuffle all the rows the same way we shuffled the labels, so that each label really corresponds to the right feature values here. So the first label corresponds to this first row and so forth. Oops, it's a lot of stuff here. Let me delete this. So yeah, we are shuffling the data set now. And then after we shuffle it, we can divide it into training and a test set. So I was just using the first 105 examples as training set, and the remaining 45 examples, the remaining 45 examples for the test set. So this is the same as writing this. So in Python, we don't need to provide the number for the upper bound, basically. Yeah, let's quickly double check that this makes sense. I mean, that this worked. Let's just check the dimensions here. Oops, I should execute this first. Yeah, it makes sense. 105 training examples in the training set and 2 features. And we should then have 45 in the test set. And of course, when we do that with our Y, it should also be 105 and 45. So that's all good. Now that was a lot of work. Of course, we can also use scikit-learn to make this a little bit easier. So scikit-learn also comes with the iris dataset implemented, so we don't really have to use our CSV file. Scikit-learn has a datasets submodule that has a load iris function, which contains the iris dataset. I'm loading it here. And it also has a train test split function, which allows us to split the dataset into training and a test set. And also we can then provide our random seed here and say that we should shuffle it. And we can specify the size of the test set. So we say 0.3, which means 30% test data. And then the remainder will be training data. And 30% of 150, that should be 45, right? So we should get the same size as before, 105 training data points and 45 test data points. Let's execute this. Yep, that looks good. So we have 105 training data points and 45 testing data points. Yeah, so personally, I like to visualize my data set first before I work with it. Now, this is kind of a little bit late in this notebook, but yeah, I wanted to just go over some concepts before we do the visualization. Maybe I should have moved that to the top. Anyways, I have a convenience function that I implemented for myself a long time ago, just a scatterplot matrix. You probably know that from R. I added it to a library called MLExtend, which is personal library that I created as a grad student back in the day, implementing certain functions that I couldn't find anywhere else for Python. So it's just like a library of collected things I collected over the years. MLExtend stands for machine learning extensions. It's just because I couldn't think of a more creative name for that, and I was just adding functions when I needed them. So yeah, here I have a scatterplot matrix function which will create a scatterplot matrix. So that uses, by the way, matplotlib. So how that works is, let me explain it step by step before we look at this. Or maybe we should look at this first. So what it is showing us is a scatterplot matrix containing the histograms on the diagonal. So we have 4 features in the data set. So here I'm using the whole iris data set, not only the 2 features. So it will show me a histogram for each feature here. The sepal length, sepal width, petal length, and petal width. I provided the names here manually because the names are not in this NumPy array. So this is a NumPy array, I think. Yep. Okay. And we can just, I find it usually helpful just to look at the histograms very quickly. And I can, for example, by looking at the histograms, see that sepal length and sepal width are not as useful as petal length and petal width for distinguishing between the different flower classes. So each flower class is one color here. What I'm doing here is why I have 3 lines of code is to make the color thing here work. I'm first plotting only the examples from the first class. So class 0, I'm doing that with this indexing here. So again, I will explain that more later in the next lecture when we talk about NumPy, but this is called fancy indexing. So it will create a mask, a Boolean mask, and it has true and false values. And then, for example, if I have this array here and I apply my Boolean mask, it will only give me the values for which in the mask I have a true value, right? So it will only give me these here, and these are the ones corresponding to class 0. So that would be iris, setosa. So it's only these values here, and then I can do the same thing for 1 and 2. So what happens here is that here I'm only plotting setosa, and then here I'm plotting versicolor, and here I'm plotting virginica. I'm only giving the names, the column names to the last one, otherwise I would have a lot of column names which I don't need. So I would have them, it would work, but they would be overlaying each other basically, so it's just redundant. And the alpha just means transparency, so if I don't use that, if I just remove that, it will be a solid color here, and if I do that for all of them, if I have a solid color for all of them, I can't see how they overlap anymore. Okay, so this is just a very simple scatterplot function to get a glimpse of the whole data set. And we can also see not only the the diagonal here, but we can also see how the scatterplots of different combinations of features look like. So sepal length and sepal width, they actually are not too bad if you combine them. So you can see, for example, I can separate out these flowers here. I should have included a legend, but I forgot. But yeah, so this is, I think, virginica. So we can separate out virginica if we would draw a line like, a line like this one. However, we can't really separate here the orange and the green ones. However, if we look at petal width and petal length, this is actually a good combination of features. We can actually draw a line here to separate these out, for example. Any case, in practice or for this tutorial, we'll be working only with petal width and petal length because I want to show you some other plots later, and these plots only work with two-dimensional data sets. So you have a scatter plot of only the two features we are looking at, or we are working with for the rest of this tutorial. Here I added the legend with the labels. So here I'm also only plotting the training set, not the whole data set. Yeah, and that is how my training set looks like. Yeah, like I'm saying here, in this case, it may be overkill to use the scatterplot function. We can just create a scatterplot using Matplotlib directly. So if you want to use Matplotlib directly, there's a scatter function and it will make a scatterplot. And here we use a very similar concept. We use the fancy indexing. This gives us all the examples for label 0, for class 0. And the second number here, this means the column. So the column in xtrain. So the first value before the comma is the row, and the second value is the column of this matrix. Xtrain is a matrix. So here I'm plotting the row, which is petal length. And here I'm plotting it against the petal width. So I'm plotting petal length against petal width. And I'm choosing a marker. This is just a circle. And for the second one, I'm using a triangle. And the third one, I'm using a square. So here, this is this is setosa, this is versicolor, and this is virginica. Yeah, and this is how it looks like if I would just use Matplotlib. Of course, we can also use the alpha, may be helpful. So alpha is usually for transparency. So we can use alpha, let's say 0.5. So then we can see, for example, there was actually an overlap that we wouldn't have seen otherwise, this one here. Now let's get to the interesting part, the machine learning part, because all of that before was just exploratory data analysis. So let's now get to the machine learning part. In scikit-learn, there are many different classifiers and regression models. So here, because the lecture was about k-nearest neighbors, we are starting with a k-nearest neighbors classifier. We could use, there's also a k-nearest neighbors or k-neighbors regressor. So there's also a regressor, but because this is a classification data set, we will be using, of course, the classifier. And there are lots of options in scikit-learn. So for each type of machine learning model, there are different options. Here we are setting the options neighbors 3. Also, yeah, scikit-learn is using an object-oriented approach. We will talk more about this when I talk about scikit-learn next week. So next week I will talk a little bit more about how the API behind scikit-learn works. But yeah, in a nutshell, usually we import a class. So this is a class. By convention in Python, we use the camel case. It's called camel case. That is when you have these capital letters. This usually denotes it's just a convention that this is a class, not a function. And so yeah, we import this k-nearest neighbors class or k-neighbors classifier, and then we instantiate a new object. So a class is kind of like a cookie cutter, and with that we are cutting out a cookie right now, and our cookie is the KNN model. And the KNN model is just an empty model right now. It's just initialized, and we say we want to have a k-nearest neighbor model with 3 neighbors, and then we fit this model to the training data set. By the way, if you want to know all the options, you can, I think you can do it like this. So in Jupyter Notebooks, you can use this question mark and it will show you all the different options. So it will explain all the options to you. So here's also the bold tree, KD tree, brute force approach that I talked about in the lecture. Yeah, lots of stuff going on here. also examples. I personally usually use the website, the scikit-learn website, because it's nicer to read. But if you are in a hurry, for example, or if you just want to briefly look up a name, I usually use that this approach here using the question mark. Okay, so this will fit our data set. So also note there is no output here really. I mean, the output is just the object itself. It will return KNN model, but we can also just suppress the output like that. Because it's an object-oriented approach, it will fit the model in place. So there's like a side effect here, so the model will be fitted after that call. I just see I have a question here in this notebook. And yeah, you can maybe answer this question by using this approach here, and then seeing where the distance metric is defined. I will leave that as an exercise. So read through that, and somewhere here, I can already see it, but I won't tell you because it's an exercise. So maybe read through this and see what, by default, what metric it uses, what distance metric, and then you can maybe have a make a comment on Piazza and have a small discussion. So let's see who gets it right first. Okay. Now, after fitting the model, we can make predictions. So for each model that has been fit to a training set, we can use the predict method. And usually we are interested in making predictions on the test set, right? So this is now evaluating our model. Also in practice, we pretend the test set is new data. So y_pred, this contains now our predicted class labels. So this is what our model predicts. How do we know whether the predictions are good? We compare them to the true labels, right? So the true labels are ytest. So we compute how many of them are correct. For that, we can use Python. So we can use a direct comparison here. It's comparing the two arrays, and it gives me true and false values. And I can then simply sum up. I can do a NumPy sum over the true values. And in Python, I should say true evaluates to 1 and false evaluates to 0. So here the sum will compute the number of true values basically. So it will give us a count of how many are correct. So 43 are correct and 2 are incorrect. All right, so doing that, so here, I see I wrote it like this, it's the same. So we can also write it like this, it's the same thing. So now in order to find out the accuracy, we have to divide by the total number of examples. And the total number of examples is the length of the array. So if you recall, shape looks like that. There's this, it's a tuple, so there's this comma. I use the 0 to get rid of the comma here. And this gives me the proportion of data points that are correct. And then I multiply it by 100 to get the accuracy in percent. So I'm doing that here. And I see, okay, I have a 95.56% accuracy. By the way, I'm using an F string here, and that is a feature that has been added to Python recently. I honestly forgot it was either Python 3.6 or 3.7. So if this doesn't work, you may have an old version of Python. So you may want to consider updating Python. But yeah, if you can't or don't want to update Python, you can also use the older approach, this classic way of making strings. Personally, I grew up doing this, and I'm also like a C and C++ programmer, and this is like a very common way of formatting strings. So in that way, I may still sometimes use in my code also this old approach. There's nothing wrong with it. I just like F strings because you can do cool things with that. You can do, for example, I don't know, you can have something like, I don't know, 1 plus 2 equals, and then you can actually have a computation right here. Oops, forgot the quotation mark here. You can have the thingy right here instead of having a separate result here, a variable, and then, or you could actually do it like this too, but oops, see that you have to have extra parentheses. So with f-strings, if you have a lot of stuff going on, so if you have another thing and another number, you have to add, or you have to keep adding these numbers here, and then it gets kind of complicated. You have to see, okay, what is going here and what is going here. If you have, let's say 10 numbers or something like that, if you have these f-strings, it's just simpler because you can put the numbers here in directly, right? So you can have also variable names. So if I have a var variable name here, let's say call it var something, I can put the variable here and it should work. So I can't mix and match things, but something like that. So I kind of personally like these f-strings, but it's not a big deal not to use them. So again, sorry, I'm getting distracted here. What's more important than f-strings though is in scikit-learn there's also a score function. And for classification algorithms, by default, score will also compute the accuracy. I think for regression models, it computes the R-square, coefficient of determination. So here though, because we have a classification model, it will also compute the accuracy. Here I'm manually multiplying it by 100. And by the way, this one here is just to limit the numbers of the numbers after the decimal point. If I remove that, it will give me the full precision, which is sometimes maybe a little bit too much, right? So if I remove that thingy here, you can see also it's the same result. So score provides or computes the accuracy, so we don't have to do that manually every time. But this was just to illustrate how accuracy is computed. Lastly, to wrap up this probably already long lecture, I didn't check the time, but we are probably already like, I don't know, 20 minutes, half an hour or something. So the last thing, another convenience function I have here, and this is also more for, I would say, educational purposes, is a decision region plot. And this is why we only work with 2 features here in this notebook, because we can make a nice scatterplot, right? So here, this is how the decision regions look like for the training set. And the decision regions for the test set should look the same, right? So it should be the same decision regions because, again, during testing, it's using the training set. However, you can, so the data points overlaid here are a little bit different. So you can see these are the test data points and these are the training data points. So it looks like to me, if I look at that, it gets all of these blue ones right, the setosa flowers. However, I can see in the training set, it gets these 2 triangles right here. So it's fitting it very well. So this green one is maybe not fitted very well because it's like a 3 nearest neighbor model. If we would use a 1 nearest neighbor model, let's maybe just quickly do that. Let's use a 1 nearest neighbor model. You can see it will get all of them correct, but then the problem is overfitting, right? Because now we make mistakes on the test set. So that was also the problem that we had earlier, or what we saw before I re-executed the plot above. It was fitting maybe these triangles too closely, and here the training test set, there are 2 circles in with these feature values. So here it would make these 2 misclassifications. So if I look at that, now I think the overfitting may be even worse. Oh, not really. So it's the same. So we also get these 2 data points right because we can see that these are tricky because they just, I mean, the training set is maybe not the greatest training set because here these are hard to distinguish just based on the training set. So if we look at our plot here, these are probably these points here. But yeah, that is also easy to look at because we have a 2-dimensional data set. In real life, we usually have very high dimensional data sets, so we would not be able to look at these plots here. But let me go back and maybe let's just compute the training set error. So the test set error is 95%. It doesn't matter, we saw whether we use 1 or 3 nearest neighbors. So we can also compute the training set accuracy. And it should give me a higher accuracy, I think, yeah. 98 here, we get more right. So in that way, it's slightly overfitting. So the model is slightly overfitting the training set. Yeah, you can maybe also by yourself experiment with other values for k, maybe k equals 5 or 7, and see how that affects the decision boundary. But now, yeah, let me wrap up this video because it's getting too long. Yeah, and then next lecture we will talk a little bit about Python. I already evaluated the survey that I sent around. Most people seem to have used Python, but I think it still doesn't hurt to just maybe at least show you how you can install it. And I also posted some exercises on Piazza that you can do to kind of familiarize yourself a little bit with Python. Okay, so I will see you back next lecture.